So, good morning to you all. Welcome to today's colloquium. So, we are pleased to have host the Professor Jacques Laskar from Paris Observatory, more precisely from the LT laboratory, the Laboratoire pour l'Espace, which until 2024 was the Institute for Celestial Mechanics and Ephemeridis computation. So, Professor Laskar is a mathematician and an astronomer, and we can say that his work has reshaped, transformed our understanding of the long-term dynamics of the solar system. And without any doubt, we can say that one of his fundamental discoveries was the demonstration in 1989 that the motion of the planets in the solar system is chaotic. So we cannot predict the future motion or the past of the planets very precisely beyond a certain time, we will see is more or less tens of millions of years, some tens of millions of years. So this was a major step in the classical question of the stability of the solar system that was initiated by Newton, Lagrange, and Laplace. And in more modern terms, we can contextualize this discovery in the framework of the Kolmogorov-Arnold-Moser theory, or the theory of Arnold. So, Professor Laskar is a member of French Academy of Science since 2003, if I'm not wrong, and he's received several recognitions as the silver medal from the CNRS, the French Center of Scientific Research, that was in 1994, then the Brouwer Award from the American Astronomy Society, 2006, and lately the Milankovitch Medal in 2019 by the European Geoscience Union. And about the geology, in recent years, Professor Laskar has focused on this AstroGeo project, which is funded by an advanced grant by the European Research Council. And the goal of this project is to study, to exploit the geological sedimentary records to infer information about the past motion of the planets in the solar system. So to try to reconstructing the past motion, past trajectories of the planets beyond the predictability horizons, which is set by the chaotic nature of the motion of the planets. So before leaving you the ground, the floor, some words. Yeah.
Thank you. Good afternoon, everybody. On behalf of the director, I would like to thank you, Professor Jacques Laskar, for coming here and for being part of this colloquium that is paid for students. So I hope that the students that are here will profit from this, for sure, from this seminar, and also the colleagues. And to thank you, we would like to give you as a present the map of the department, just to remember us, and thank you for coming.
So thanks a lot for this introduction. And just before starting, I would say that mathematicians are mostly interested by the method very often. I'm not so much interested by the method, but by the object and by the results. And to understand the dynamics of the solar system, in the first stage for me, it was understanding dynamical system. So Federico mentioned Kolmogorov-Arnold-Moser theory, and this was it. But after some time, after some understanding, then I want to understand the real solar system. And to get the real solar system, I had to go beyond simple approximation, and also I wanted to go to observation and to get really the true trajectory of the solar system, not only in the recent years, but also in the distant past, beyond the horizon of predictability that is imposed by the chaotic nature of the system. This is why in this project, in fact, it will be very dirty for mathematicians, because you go to work with geologists, and not theoretical geologists or geophysics, but geologists that dig into the ground. Because it will be into the ground that we will get the information for the past evolution of the solar system. And I had many collaborators that I could hire, some of them within the AstroGeo project, as it was said. And the very important thing about this ERC is that it gives you a lot of flexibility. So I could hire one day a pure geologist, and the second day a mathematician of statistical analysis, and the third day an engineer in computer science. So the AstroGeo project, the goal is to recover the history of the Earth, the history of the Earth-Moon system, and the history of the full solar system through geological sedimentary data. The idea is that the planets interact between themselves. This modifies the orbit of the Earth, this modifies the climate of the Earth, and as it modifies the climate of the Earth, it modifies the sediments that are accumulated in the deep sea. For a long time, so we tried to get the best possible evolution of the planetary motion, and it was used by geologists in order to calibrate the sedimentary record. But here we want to do the opposite. We want to use the geology to impose some constraint in the past evolution of the orbit of the planet. Just to remind you, very simple thing. So in first approximation, that basically the celestial mechanics of Kepler, that was in the 1609, the planet moved on an elliptical orbit. So it moved on an elliptical orbit. The ellipse is practically the relative distance between the two focus, and that's the eccentricity. And there is a very simple formula that you will not find it very easily, but it's very simple. This says that the relative temperature variation between the time when you are the closest to the sun to the time where you are the furthest to the sun, this relative variation of temperature is equal to the eccentricity. This is what you obtain when you take a simple model of a black body and make the equilibrium between the input radiation and the outer radiation. So you have this very simple formula, but here T in fact is in Kelvin. So T is about 300 degrees. So you see that even with the present eccentricity of the Earth, that is very small, 1.7%, it already gives you 5-degree difference. Of course, you know that we are not in summer when we are in the closest distance to the Earth. We are in winter at this time. We are at the perihelion in January, because the seasons are dominated by the obliquity of the Earth. There is not the same season in North Hemisphere and in South Hemisphere. But this makes a change that compensates at present this change of temperature between, so it reduces the contrast between winter and summer. And when the spin of the Earth precesses over 20,000 years, it changes when it has the 180 degree difference. Then you have the summer when you are at perihelion, and it increases the contrast of the season. This is for the present eccentricity value. But the eccentricity, as I said previously, is changing. So it can go up to 6%, and in this case it's 17 degrees. So here you see that it's quite a lot, and you understand that it could leave some trace on the surface of the Earth. And in fact, this is what the foundation of Milankovitch's theory of climate. which is more complete than just eccentricity. It takes into account the fact, the seasonality, because it looks to the insolation in summer in high latitude. And you see that you can have a 20% change in this insolation in summer in high latitude, depending whether you have the summer when you are the closest to the sun and the summer where you are the further. And depending on the eccentricity that modulates everything. So the grain curve, the insolation, is modulated by the precession, and altogether it's modulated by the eccentricity. So you have the precession period, 20,000 years, and in eccentricity you have two main periods of 100,000 years and 1,400,000 years. And you have also the fact that the tilt of the Earth is also moving with 40,000 year period. And this is now recognized as the main factor for the big change of climate in the past, like the Ice Age. So this is why it's important. You can see that if you want to recover the past climate of the Earth, the variation, you need to make a solution, astronomical solution with celestial mechanics that is able to recover the past evolution of the orbit of the Earth. And that was done very early. The first solution was done by Lagrange in the 18th century. So you see, so Lagrange, at the time, he has only 6 planets, and it was basically a linear approximation. He compute the perturbation, but he developed a series of eccentricity, but keep only the term of degree 1. So he ended up with a linear system of differential equation and show that he can get a solution in form. You know how to solve this kind of system. You diagonalize the system. You will have some frequencies that are the eigenvalue. And in fact, these frequencies have periods that go from a few tens of thousand years to a few million years. And this is a long-term evolution of the orbit of the planet. So he's the one who made the first computation like that with this two 6x6 matrix, so 72 terms of degree 1. And then this was improved by some further computation. But you see the progress is very slow. Using computer, implementing the analytical computation, so in 74, Patavinum did a solution with additional non-linear term. There were 300 terms. And in fact, 10 years later, I pushed this to very far. It was one scale beyond, with a very huge system of 150,000 terms. And then there was a numerical integration. So you see, this is perturbation method. So when you do perturbation method, you practically write that the Hamiltonian, so the energy of the system, is the Keplerian part. The Keplerian is one planet around the sun, so the motion is elliptical. This is integrable. Plus the perturbation, that is the perturbation of the planet among themselves, which is small. There is a small parameter because the mass of a planet is much smaller than the mass of the sun. So you have this expression, and then we make expansion of the solution in order of epsilon. And in this case, you do some averaging of order 2. I will not enter into the detail, but you end up writing this, computing this expression, where the Poisson bracket here is the product of the partial derivative. So it looks like that, it looks relatively simple. But the problem is that you have a lot of variables. You have 8 planets, so you have 4 secular variables by planet, so it's 32 variables plus 8 longitude and 8 semi-major axes. So it's a lot of variables. And when you end up with polynomial in 32 variables, even if you go up to relatively low order, which is in this case 6, the number of terms blow out very rapidly, and you have 100,000 terms. In fact, I did that in '84, and at the time, I would say that even now, it's not trivial to put this computation on the computer. If you try to do that on Mathematica or on Maple, you will have some hard time. In fact, nobody has done it yet. But at that time, I could do it in less of 2.5 megabytes of memory. And this system doesn't describe the motion of the planet. This system describes the deformation of the orbit. You forget about the rapid motion of the planet on its orbit. You just describe the slow deformation of the orbit. So now we can compare these various solutions. And I put here the solution of Lagrange in blue. You see, the solution of Lagrange for the eccentricity of the Earth. All solutions start with the same initial condition. Over 1 million years, it's not bad, in fact. It's qualitatively, it's very good. You get already the main feature of the solution with this 400,000 year period and 100,000 year period. And then I mentioned the solution of Bretagne here in black, but you see some discrepancy. And then this green solution is the solution I did with this very huge secular system of 150,000 terms. And then much later we could do some direct numerical integration, and it is the solution in red. And if you look to the two latest, they are here, you see there is basically no difference over 1 million years. The big difference is that the secular equation, they go 1,000, also the system is huge. You see 150,000 terms, 1,000 polynomial terms of degree 5 in complex variable. It's a huge system, but it is organized in such a way that you can evaluate it very rapidly. And this integration is 1,000 times faster than this one. So indeed, when I did that for the first time, there was absolutely no numerical integration to be compared with. Here is the status of the main numerical integration. So numerical integration is much more easy. You take the gravitational equation, Newton's equation, so it's one line, plus general relativity, you add two lines, and you put them in the computer. And you integrate it numerically. The only problem is that you need a very small step size. You need a step size of a few days. You see here, the step size is 0.7 days. Here it's 7 days. So in the circular equation, the step size was 500 years. That's a big difference, because you are integrating only slow motion. And at the time I did this computation, the only numerical integration of the full solar system was done only over 4,000 years. So there was nothing really to be compared to. And you had to wait until 91 to get the first long-term integration of those 3 million years, and only into 92 about 100 million years. So you see, I will show here, in fact, different kind of integration. This one, the first one, is you take Newton's equation, as I was mentioning, and general relativity, and you can do it, you want to have the most precise solar system, so in this case you put everything that makes some perturbation on the planet. You take the asteroid, you take the moon, you take the shape of the moon, the shape of the Earth, everything. And in this case, you have a step size that is about 500th of a day. And it takes 1 day to integrate 50,000 years. This will be the model, the most precise model we do at present, that is directly compared to the observation. Then, if you want, but this one you cannot integrate it over a million of years because it's too slow. So you make some simplified model, you use symplectic integrators, and in this case, you can take a much longer step size and integrate 5 million years per day. And that would be quite what is commonly used now for long-term integration. And then this is the original computation I made. You no longer integrate the motion of the planet, you integrate the deformation of the orbit. That is, basically you integrate the second focus of the orbit, and you end up with this quasi-periodic motion. And in this case, in one day, you make 5 billion years. So, and this hierarchy is still valid now. So despite the computers are much more powerful, if you want to do statistical analysis of trajectory over 100 billion years, you'd better use that than this, because otherwise it will be much too lengthy. So this is for the, I would say, for the theory, for the practical, how you can integrate the planet, the motion of the planet in the solar system. But now I want to look to the observation. An observation over a very long time. So I told you previously that as the eccentricity change, you will have some change in insolation on the surface of the Earth, and this will have some effect on the climate of the Earth. And you can recover that. You can look, for example, to the ice core. This is an ice core. You see, it's 3 kilometers depth. That's in Antarctica, and it represents about 400,000 years. So you have this index here, which is a ratio of oxygen 18 over oxygen 16, and this is a measure of the global temperature on the Earth. So you see it was either more, more warmer or colder. I think it goes the other way. This is I don't remember which way it goes for the temperature. So, and you see that this curve is very similar to this curve, and this is the insolation curve at 65 degrees north latitude. So what will people say? They will just, here you have depth, you don't have time. Here, this is celestial mechanics, the motion of the planet. So you have a solution with respect to time. What people will do is they will say that this maximum corresponds to this maximum, with eventually a small offset, but basically this is what they do. And like that, by fitting these, then you will make a transfer between time and depth. To recover like that with time scale for this ice core. And you can do that. This is for ice, but ice go only over 1 million years. You can go much further if you look to sedimentary record, like this one that is drilled in very deep sea. You go to deep sea because you want some deposit that is not disturbed by tempest or whatever. And you recover, basically you have a ship like that that will go in a place where there is 3 kilometers of water. They put 3 kilometers of pipe, and then they drill for 1 kilometer. So it's quite a lot of pipe. And at the end, they get the core like that, which is 10 centimeters width. The width is 10 centimeters. And they cut it in slices of 150 centimeters. And you see the color is changing. But here you don't see much. But if you put them, stack them together, like that, you put them like that, you have this alternation of color, and you can match it very precisely with this maximum of insolation. So when you do that, you have again, here this is the motion of the planet, this is directly celestial mechanics, and you can match, here we are at about 11 million years, you can match the sediment, so you can get here a time scale for the sedimentary record. This works very well. So, in fact, this was used in order to establish some astronomical time scale for the geological age. And the official geological age, you may not know that, for all the recent parts is now done by adjusting the sediment to the astronomical solution. So you see, in some sense, it's a kind of revenge of the astronomy against fundamental physics for time. Because before, the time was measured by the rotation of the Earth. But then, with the atomic clock, it went to the transition of a given atom of cesium or whatever. And so you went to fundamental physics for the day. But here it's the contrary. A lot of the age are measured by the decay, the radioactive decay of some element, uranium to lead, for example. But this has a lot of uncertainty. And for the most recent part here, everything is calibrated astronomically with the method I just showed you. But, so, you can say it's fine, we can make like that a geological time over a very long period. We just have to compute further, as the geologists, they are digging further and further, so we astronomers need to compute further, and that will provide everything we need. The only problem is that the motion of the solar system is chaotic. And this, as Federico mentioned, this is what I discovered, now it's a long time ago, it's 35 years ago. And this was using these secular equations. So basically, you have an increase of the error in the integration that is exponential, and that goes like 10 to the power t over 10, where t is in million of years. So every 10 million years, you lose one digit. So if you have 15 meter error at present, after 10 million years, you have 150 meter error, but after 100 million years, you have 150 million kilometer error. So you know already here that it will never be possible to get a solution for the solar system starting from the present initial condition that go beyond 100 million years, or roughly 100 million years. In fact, when with that, at the beginning, I thought, or some years ago, I thought, okay, because we were at the border of, we had a solution that we thought was valid over about 40 to 50 million years, and we wanted to go up to the end of the dinosaur at 66 million years. So we wanted to get a little bit better. So we thought, okay, we lose one digit every 10 million years. It doesn't matter. We will work a lot in order to get, every time you improve everything by a factor of 10, you get 10 more million years. This is exponential. So I thought, okay, we will do that, and we will get a few 10 of million years more in order to see how far we can go. So to do that, we did a lot of work. First, I thought that it was important to master completely the adjustment to the observation. I wanted that we had, you want to be sure that the solar system you are integrating is a real solar system. And the only way is to look to the real planet and to try to have the best fit with all the observation. So we did a very high precision model, and we use all the available observation. When I mean high precision, it means you take the Newtonian interaction between the planet, the main asteroid, you had 300 asteroids, you had relativistic correction, you had the fact that the planet are not spherical bodies, you had the moon, you had the interaction of the gravitational potential of the Earth and the moon. Basically, you had everything that will lead to a small signature into the data. So you have this big system, And you have about 150,000 observations for planetary observation, 50,000 observations for the moon, because for the moon we have the lunar laser ranging that make measure of with an accuracy of 1 centimeter between the Earth and the moon. You take all this, you solve for all the parameters, and we have this model that was improved. We started in 2003 and we have kept improving it for 20 years, including each time the new data coming from new spacecraft around the planet. Basically, the best observation you have is when you have a spacecraft around the planet, because in this case, you take the radio signal from the spacecraft to the Earth, and you can get accuracy of a few meters or a few 10 meters in the distance, which means 10 to the power 10, 10 to the power 11 precision. So we did all that, and the latest measurement we had was the one of given by the Juno spacecraft that went around the Jupiter. And with all that, we could improve the precision of these ephemeris. You see, in the old time, the precision here in kilometer of the ephemeris was of the order of 1,000 kilometers. And then with the first improvement, you had something that went to a few kilometers. And then this was already in 2011. And you see, everything of the order of the meter, except from Jupiter, that was still with an error of 2 kilometers. But with the Juno mission, we got a few meters also for Jupiter. So basically, we have a very precise, we worked 20 years to make a very precise model. We are sure that it fits to the real solar system. But then we wanted also to improve the numerical integration. So we devised new integrators, and these are symplectic integrators. I will not devise that, but in order to compute this symplectic integrator, you have to do a Lie algebra computation and to solve algebraic equation after that in an exact manner to derive this integrator, because basically you have to split the integration of your system in several steps, and you will have two parts, the main part and the perturbation, and you will alternate the integration of one and the other one, so you are commuting some flow with something that is not commutative, so you will have to have some Campbell-Hausdorff formula if you know what it is, or if you don't know, you will learn. And with that, you can derive very precise integrators that are very stable in time. And this is what we use, for example, in 2004. Because not only you need very small error, but also in the implementation, when you implement your integrator on the computer, you need that the error is random. You need, because it's very easy when you implement something to have a small bias in the implementation. So and this, for example, is the PDF of the error, and you see that it's a perfect Gaussian, so we know it's random. We had this already in 2004, and we have made a lot of work to improve that to higher order. So we gained about 5 orders of magnitude in precision to get some new integrator of higher order. In fact, this development of symplectic integrator of high order has been a whole industry now. So we did all that. We did all that in order to get, you see, I remember what we wanted to get. We want to get a few order of magnitude better in order to extend the duration of the integration. And we did all that and we failed. We failed because of two bad guys. And these two bad guys are Ceres and Vesta. Ceres and Vesta, they are the biggest of the asteroid, but they are small. You see, Ceres is 1/6,000 of the Earth's mass. Vesta is 1/22,000 of the Earth's mass. And so they are very small. It's nothing. But the problem is that before our work, people were looking to the motion of Ceres or Vesta perturbed by the planets. If you look at that, you find that the motion of Ceres or Vesta is regular, or at least it's not as bad as the planet. But they didn't take into account the mutual perturbation of Ceres and Vesta. But when we put them, our surprise was that in fact, the motion of Ceres and Vesta is highly chaotic, much more chaotic than the planets. You see, this is how we increase the difference between two solutions of Vesta when you don't put the mutual perturbation. So basically, it's a logarithm, so which means it increases very nicely. And this is how it goes, because we are in a logarithmic scale here. Here is how it goes when you put the mutual perturbation. So you have an exponential divergence. You have a chaotic behavior here, not with a time scale of 10 million years, but with a time scale of 50,000 years and less. Because they have close encounter. So their chaotic motion is not due to secular interaction, long-term interaction, but to rapid interactions. And because of that, you see that after 500,000 years, and even much before, you don't know where they are. If you don't know where they are, you cannot predict how they perturb the planets. So there is an incompressible uncertainty that you will never be able to master. And the final limitation of the planet motion will be due to this one. And you see here, we have here a few solutions that start about the same. This is not the full solution of eccentricities. It is some components so you can see what it is. Over 50 million years, they all give the same thing. And basically, after 60 million years, you have nonsense. And this is this limitation. So this tells you that right now we have a solution that is valid over 50 million years. And I can tell you that you will never be able to get a solution beyond 60 million years from the present initial condition. And when I say you will never, I mean you will not be able to do it now, but in 1,000 years you will not be able to do it either. It's not something that depends, it's due to the intrinsic dynamics of the system. So you can say, what he's saying, how can he say that in 1,000 years you cannot do that? But it's like the meteorologic prediction. You will not be able to predict the weather over 3 months. It's the same thing here, but at a different time scale. Or if you want something more precise, you can say that I told you that right now we have a 15-meter error, for example, in the initial condition, in the position of the planet. That's about what we have now. And this leads to an uncertainty, the total uncertainty after 60 million years. So, as you say, or he's saying nonsense, we will improve everything, like what I was trying to do previously. We will improve everything by 3 orders of magnitude, which means instead of having 15-meter error in the initial condition or in the model, we go to 15 millimeter. Which means we take into account a huge amount of small planets in the solar system, and we have to take their interaction into account. So we go to 15 millimeter precision. What do we gain? how far we will be able to go. You see, the problem is that the limitation will not be given by the motion of the planet. It will be given by the motion of the asteroids, Ceres and Vesta, which are the ones that limits. So what will be the gain? How far we could go then? Does someone dare to say yes?
150,000 years.
Yeah, what?
150,000.
Yes. The only thing we will gain will be 3 times this 50,000 years, so we will go up to 60,150,000 years. And assume you say, oh, we will do much better. We will work for 1,000 years and improve everything by another 3 orders of magnitude. And we are going not to 15 millimeters, but to 15 micrometers, which means you take tens of thousands or hundreds of thousands small bodies in the solar system, the motion of the star, everything, and you need to have all this with a large precision. How far will you go? Now everybody, I hope, can give the next answer. I'm waiting for your answer. I will not go on until I have. Yes? Yeah. The only thing you will get is this. So you see, exponential barrier is very steep. And this is really a practical limit. So this is why you can say that you will never be able to beat that. And still, of course, I tell you it's impossible to go beyond 60 million years. So what do we want to do? We want to go beyond 60 million years. We want to go beyond 60 million years because we know that the Earth is older than 60 million years. We want to know what was before this 60 million years. And we cannot propagate the model. This we know from what I just showed you. I will not say that what I just showed you is complete nonsense. No. I will show you how we can go beyond 60 million years, owing the fact that by the method I just showed you, we cannot go. And there is another thing. The problem is sometimes I don't want to have some. Don't want to describe a model of the solar system. I want to describe the real solar system. The solar system has only one history, and this is what I want to go. I want to get. And eventually there could have been a star passing by in the solar system that changed a little bit the orbits. I want to be able to state whether this occurred or not. I want to be able to say whether in the past there was another planet in the solar system or not. So this is why the only way to go now is to add some information. With just the present time information, we cannot get the answer. So this is why, in fact, we want to go back to geology and to get the information from the geological record. And of course, you would think, and I think, in fact, that, okay, geology is nice, but it's a lot of mud, very uncertain, so we cannot get much out of it. Because here we are speaking of celestial mechanics, the most precise science. I was mentioning you 10 minus 10 precision, 10 minus 11 precision. But now we want to look to this pile of mud and look back to this geological record. So this is the same record I showed you previously. This is the score, and this is basically the color here. And you see, this is the precession, not the precession, but the insolation, or roughly of the insolation. Typically, what was done before was to match the minima, like that. You see this minima, go here. And here, this is depth, this is time, and like that, you match time with depth. You have an astronomical solution, stratigraphic data, and you get the transfer from time to depth. So you establish a geological time for an astronomical time for the record. The only problem is the one we are facing now with what do you do when this astronomical solution is not available? And also, as you have very often, you have some bit in the you can have two periodic components that will make some bit like that. So of course, here you may see some outcome because the amplitude is large, but when the amplitude is very low, you have no signal at all. So that's another problem in the geological analysis. So what we want to go is to go beyond that, and this is what we did in this method. We want to start from the stratigraphic data, and we want to get without any astronomical solution, because we cannot rely on any astronomical solution. We want to get both the time depth transfer and the astronomical signal, just from the stratigraphic data. And we will do that using some genetic algorithm and statistical Bayesian method. So, yeah, I just say here that this is, we release that as a full open source package, but this is not really what you will jump on it. So I will show you how it is done. This is done. What you will do is you will assume that the signal you are looking in the geological record is obtained by some forcing astronomical signal, the insolation, and some random noise. But the astronomical signal, the insolation, you can model it as a sum of periodic terms in the first approximation. But we will not impose much. We will just say, we will just search for something that looks like an astronomical solution. So just a few periodic terms. We just say that the astronomical forcing will be something due to eccentricity, something due to precession, something due to the tilt of the Earth. So basically a sum of periodic terms where the frequency will be the secular frequency which I mentioned when I mentioned the solution of Lagrange with the eigenvalue of the linear approximation. So you have some period of very low, some frequency of very low period, but this is the forcing. The forcing is with respect to time, but the data is with respect to depth. And the data is your forcing signal, depending on time, that depends on depth, plus some noise. And a lot of noise, in fact, in this case, a lot of noise. So, in order to do that, we will determine at the same time the amplitude, the frequency, and the phase, but also the time depth function. We determine at the same time a time depth function that makes the transition from time to depth. So the way to do it is, of course, a function. It can be any function. So we will model this function by just a few points and some interpolation between these points, because we cannot handle infinite number of parameters. So we limit the number of parameters by doing that. And I will show you, the first thing is to benchmark things. So we do it on data that we make fake data, so we know what is in it. To do that, we make something that looks like an insolation, that is eccentricity plus depreciation plus climatic precession. So it's an astronomical signal, here 1 million years. Then we will model, yes, the difficulty in this time depth function is that the sediment don't accumulate in an even way. The accumulation, the sedimentation rate is changing all the time. So we want to determine this function, this sedimentation rate. The time depth function is just the integral of the sedimentation rate. So we take a sine curve as our model sedimentation rate, and we will see, are we able to recover this from this? Of course, this is too clean. We want to have something that looks more like geological data. So we add as much noise as we have a signal. So you have your data like that, and then you search. So the way you search is you will take some random sedimentation rate, and you will make some genetic algorithm that will search. Each time you give yourself a sedimentation rate, and then you search for the best possible astronomical approximation of your signal. And you evolve like that. This is how it goes. You see, you search for this curve, and at the end it works quite well. At the end you get that. You see the true value is the dotted line, and this is what you get. Usually the precision deteriorates at the end, and we get even certainty on this parameter.
Sorry.
Like that you can enjoy. Okay? And in fact, it works relatively well. And then we thought, okay, this is a very simple change of sedimentation rate. So we can go to different function and see if we have a step, can we recover it? And you see here, we are recovering it quite well. If you have so curve, you recover it. But of course, you have some uncertainty that is larger in the peak here. And again, various examples. And but geological data are very nasty usually. This is easy because this is you already, even if you make a lot of noise, it's already more easy on fake data like that than on real data. And for example, some referee told us, but what about the hiatus? The hiatus is a big thing in geology. It is the fact that sometimes you have a record, but there is some missing part. Because it has accumulated, but there was some accident, and a big part was removed, and then it continued to accumulate. That's the usual, you see, in mathematics, the big question to ask is what happened in the non-commutative case, or what happened at the border. Here in geology, it is what happened with the hiatus. So it's a question you can ask even if you don't understand anything. But, okay, we took the question seriously, and we looked to what happened if you make a hiatus. So in this example, you take again the mock data like that, 1 million years, and you cut 100,000 years. You cut 100,000 years, and then you splice it, okay? You glue it. So here, it is the same thing as this one, but there is 100,000 years that is missing. We don't say anything, we don't tell anything to the software, and we just look how it goes. In fact, it recovers properly this hiatus. What it does is here, you see, you have the real transfer function, which is this one with a step, and what we recover is something that is basically a smooth transfer function. Because what will happen is that you have one missing part, but you are constrained by both ends. So you will still get something. And in fact, hiatus, as long as it is not too big, of course, if you suppress everything, you don't. But here, up to 100,000 years, it works pretty well. Then, how is done the search for the function, for the sedimentary function? It is done by in an iterative way. You don't search because you have to select the number of nodes you use in your function, and you don't want to start with a big number of nodes. You start basically with 2, which means a linear function, and then you increase the complexity. Here 2 nodes, 8 nodes, 16 nodes. You see the true function is a red curve, and at the end, you can go like that, but the uncertainty will grow. And in fact, you have some statistical indicator that basically you don't want to add too many parameters, so it tells you when it's good to stop. So here it was 24 nodes. So you use this statistical indicator, and what do you get at the end? You get that. So this is the black curve was the initial data. Okay. The red curve, the blue curve is the true signal before adding the noise. And the red curve is what we recover. And more important, from this recovered signal, what is the eccentricity of the Earth? So the red curve here is the true eccentricity, and the black curve is the eccentricity that is recovered directly from the data with the uncertainty in gray. And when you have this curve, so I think it's quite amazing, but still not here, because here it is still synthesized data, always more easy, but you recover with 96 correlation coefficient. And once you have this, here you have determined the local time scale. You can slide, you take your black curve, you see basically you take your black curve and you slide it over, here you have the solution, which is the red curve, we know it. So you slide it and you see when the correlation function is, the coefficient is largest, and it gives you an absolute time scale. So you recover both the local time scale, and then if you have a solution, you get a global time scale. This is on experimental data. So this is on data, because it's the first thing to do. You want to see, is the method working when you know perfectly the solution? But of course, the noise, the problem in nature is that you don't even know if all these assumptions are true or not. You don't even know if there is some astronomical signal recorded in the rocks. You don't know if there has not been a lot of the parameters that have changed everything, and that you are just analyzing noise. So we went then to the real data. So this is the real data. It's the same code that I was showing you at the beginning, and this is again the way it was done previously. You see, trying to establish a time scale here by matching the peak, and this was done by Christian Ziden, which I know well, he has been a postdoc in my lab, and this is what he did as his PhD thesis. So it took him 3 years to do that, basically. And so we took this record and we put them in astrogeophyte. And this is the inverse sedimentation rate. So the red curve is the one that Christian determined by this peak fitting. And then we let the software go and make the automated analysis, starting with 2 nodes, so linear curve, and then increasing 12, 24, 36. And in this case, the indicator, statistical indicator, tells that it is 60 that will be the best equilibrium between number of parameters and uncertainty. So you see, the first thing you see is that we recover quite something that is very close to what he found, and except here. But in fact, we discussed with him, and in this case here, it's not obvious who is, because it could have been that he would say, oh, but no, here we are absolutely sure that for some other reason, the solution is this one. But it's not the case. Here there is some uncertainty, and our solution may be as good. In fact, give a better result at the end. And what do you get for the eccentricity? In fact, you get this black curve again. So your black curve is the eccentricity that is obtained directly from the record, from the sediment, with nothing else. And this is in a period 10 million years when we know well the eccentricity of the Earth. So we can compare it directly with the real eccentricity. And you see that the match is nearly perfect with the 0.82 correlation coefficient. So I must say I was amazed to see this, because I never thought it would be possible to have such a quantitative result out of this pile of mud. You see, with the information that is practically the color of the mud in this sediment. And here you recover something that is as precise as what you get with celestial mechanics. So this is over, you see, 6 million years. And we did also some false alarm, what's the name? False alarm. Yes, false alarm probability. So basically, to know if there is a signal or a noise, you just take your data, you make some noise with the same property as the noise of the data, and you analyze it. And if you do that, this is what you get, the blue Gaussian. And this is the analysis of the real data. And you find that you are several sigma away from the noise analysis. So with a false alarm probability of 1 × 10⁻⁶. And in fact, apart from this place at the end, we recover roughly what they had before, except, but here with uncertainty, with everything, and a difference in this place. Another record that is given here, it's an older record. And it was done by Thomas Westerhold. This is some drilling here in ocean drilling. And it's from 40 million year old. So here again you have the old, the one that Thomas obtained. And we discussed with him directly. I know him well also. And he told us basically that it took him 15 years to obtain the red curve. And so we just let astrogeophyte evolve, and we get this function here also with some discrepancy. But again, by discussion, it's not. It doesn't say that it's not one is not referred to the other one. And when you look to the eccentricity is amazing. Here again also, you get this black curve with uncertainty. So the black curve comes only from the data. There is no input, no astronomical input. It's just here, and you get this curve, and it's compared with the true eccentricity that we know well also, because we are still in the region where it is well known. And finally, the last one, which is this one. It's an older record, And here again, so here we stop here. It's nearly constant in this case, nearly constant, so it is more easy. And again, a very precise recovery of the eccentricity. And here we start to be at a place where the astronomical signals start to be questionable. So we used here in this work the best known geological sequence, but now of course we will go beyond. And now what I can say is the road beyond 16 million years is open because we can do that for any geological record. It doesn't matter how old it is. And the challenge will be then to match an astronomical solution that will match all these records, and also to check whether we can get coherent. Because when you analyze one record, you get a solution. But what happens if you have another record that is on the same time interval? Will you get the same solution? Because the orbit of the Earth has only one solution. But if what you have done is dominated by plenty of some other factor or some other uncertainty, then it may be difficult. And in fact, it is. We are currently analyzing that. It's not so easy. But this is at least one way to go. And I will stop here. I think I have spoken for 1 hour.
So thanks. We have some questions. Any questions from the audience?
Thank you very much for this very interesting presentation. I'm really impressed by this kind of interdisciplinary research. I have a question about resonances. Do you expect from the extension of the analysis also new information about resonances governing the chaotic diffusion of the real solar system?
Yes. Okay. Just to put in context. So the problem why the solar system is chaotic, and I will explain that more in the lecture on Tuesday, Wednesday, Thursday in the department. I will explain that. It is chaotic because of the interplay of several secular resonances. In general, you have chaotic motion when you have resonance that overlap. And this is the case, not resonance. Resonance is when you have some period, some fundamental period that is equal to another one, another combination. And you don't have, in the solar system, you don't have resonance in the orbital motion, in the fast motion. But you have secular resonance, which means you have resonance in the long-term precession motion of the planet, the one that is involved here. So right now we are in a resonance. There is a combination of perihelion and nodes of the Mars and the Earth that is in vibration. You see, a resonance will be like a pendulum motion if you are doing some oscillation, while the generic motion will be always circulating like that. You see, if you have one periodic motion, it will do something like that. If you have a combination, it will also circulate with the period that because the combination of the period of the frequency, the combination of the frequency, except that when you are in resonance, and then you will have some oscillatory motion. And the chaos comes when you go from this to this. You see, just very schematically. So here, what we want to find is we want to find back the sequence of resonance that was actually in the solar system. We know that right now we have some resonance that makes some, this resonance is visible in the sedimentary record. We can see some oscillations that correspond to the vibration of the resonance. But we want to know when was some chaotic transition. There has been some report, people in geology have looked to that, they were very much stimulated by some paper I made showing these they were looking for that. But now we want really to follow the full solution in time and to get this transition, to be able to describe practically, if you want to think of in terms of harmonic diffusion, we want to see the evolution of the solar system in the web of resonance. I'm not sure it will be possible, but it's good to have some aim.
How long do you need to go back to see this?
The first one, they occur within the first 100 million years. So, to get the first one. So this, yeah, we will get it.
Okay, thank you.
So there was another question here?
In the simulation of the solar system that you were discussing in the first part of your lecture, did you use the positions and the velocities of the bodies in three-dimensional space or in the plane?
Oh, we are in three-dimensional space, yes.
Because the solar system is actually everything more or less moves on the ecliptic plane, right?
Yeah, no. It is as the inclination are about the same size as the eccentricity.
Yeah.
So if you look to the motion, you have a lot of oscillatory motion in the plane of the orbit.
And
A few degrees, it's not big, but it's still important because it is this which induce the tilt, the change in the tilt of the Earth.
And could you use this to provide evidence that no star has passed near the solar system in the past? The fact that the ecliptic plane fits so well the position of all the planets?
Of course, you can. If there was a big change, it would be much more. The plane of the orbit could change. But what we want to show is even if there is a small change. You see, we want to be able to monitor in a very precise way. Most probably there was not some big event, but we want even to be able to monitor small change. And to state things in a definite way. You see, in the or 20 or no, maybe more 30 years ago, there was, I don't know if people have heard about, for example, Velikovsky. It's someone who looked to the Bible text and said from the analysis of the Bible text, he found that Venus has encountered the Earth 6,000 years ago. See, but at the time, nobody could say anything. It's very, when you have something that is not known, it's very easy to make some crazy scenario. But for example, here, we can be sure that something, we can prove that something like that didn't occur because we fit so well the geological record that it doesn't give space for such a fantasy. And it's the same kind of thing we want to be able to do on a much longer time.
Okay, thank you.
So, should a question?
No, maybe not. Okay. Jacques, I wish to know, in the first part, in the dynamical part, which is the role, if any, of dissipation? Because your framework is a symplectic integrator schemes work for Hamiltonian system, but there are tides, there is
That's right.
pressure.
In fact, we have tides. We have the tidal evolution of the Earth-Moon system. But the symplectic integrator, it works also very well if you have some small dissipation. It's just, you are just commuting the flow, and it still works very well in this case. It's not
Nearly conservative.
It's nearly conservative, so you can still use it. Yeah. I've not done the theory, but I've done the practice. But maybe it can be theoretic, that you can still do it.
So any other question? Nice. Question? Any curiosity?
Don't be shy.
Don't be shy. Okay. But I have a question on the last couple of slides. You showed the sedimentation rate in red.
Yeah.
And the equivalent in black for the numeric, the error Bayesian approach, the genetic algorithm. They are complete, Yeah, for
Like,
example, they are completely independent.
yes, totally.
So you just superimpose on the plot,
Yes.
they are completely
Yes,
independent.
yes.
So
Yes.
they, okay.
So
So at some point, for example,
it's
when you
true
put-
that, for example, if you look to this one here, yes, they are totally independent.
okay.
All just because here, you see the fact that this match well with this, it's totally independent.
Independent, okay. So you
So-
just superimpose
Yeah.
to-
And in fact, after we did that, we discussed with, we have the chance to, I know very well all of the geological community that do the best work in this field. So because for 30 years, I gave them the astronomical solution on which they were fitting their data. But now, when you do something like that, you want to know at the end, because you do it in a total blind way. And at the end, you want to know what is, do they have some additional information that will tell them, that will tell you that, for example, here they are certain that this is what occurred and not this. But so we discussed with them and they say, no, at this place the core is not very good and it's not of use. They say that they have a problem to say something. And it's totally independent.
And are there an example of geological samples, geological records beyond the horizon predictability in the past? We cover the same amount, the same time or less, and that are completely independent.
Yes, we are doing that now. Right now we are analyzing data that go from 40 to 100 million years. So most of them, we started at 40 because we wanted to calibrate things and to see. And the important thing, very often, to acquire some geological data like this one is not easy. It is a big work, and it costs millions or 10 of millions of dollars to make a core. So there are not so many of them, and very often people were looking to some time interval, and they will not overlap too much. So some places it's difficult, but there is, we are in fact looking for places where there are this independent core in different places covering the same time interval. Yes.
You have already some results of the consistency of the different.
Yes, we have some results.
Is that consistent or?
It will be difficult to say. It will be for the future. But we are working on that, yes. Because that's indeed
Yeah, it's amazing
some
to
important
see
question.
if it's consistent or how much it is consistent. So any other question? Positives? No. So we thank Professor Laskar again.